This is part 3 of the Backyard Roller Coaster Physics, Math, and Engineering STEM class. We left off in part 2. We're going to make a two-dimensional roller coaster. It's going to have a drop, go through a dip, have some positive G's there, go over a little peak, maybe almost hit negative G's, and then a final dip where we go the fastest. And then it'll just rock back and forth till we're done. So, the airtime hill. When you kind of get weightless right over here, when the track is pulling the cart down and your body's kind of lifting up, the cart is actually accelerating toward the center of the curve, and so as the cart accelerates away from the person kind of feels a little weightless, or maybe completely weightless, or even the negative G's would mean you actually have to hold yourself in the cart. So we do the math here. This airtime hill is the middle hill, and we want to hit about 0 G's there. In other words, the centripetal acceleration in the outward direction, the reaction to the centripetal acceleration, we want to be equal to gravity right here. And when the acceleration from going around the curve is equal to the same value as the gravity pointing down, then we kind of feel weightless. We don't weigh anything right there because the accelerations and forces cancel each other. If we do the math right and we know what the velocity is and the curvature here, we have control over the curvature and the velocity. And then ultimately we'll do all these calculations and design a track where we have predicted what's going to happen, and then we'll build it, we'll test it, and we will see how close we were. So this peak number 1, we know we want negative G's, a little bit of weightlessness right there. And so gravity in the down direction is offset by exactly what the value is of the centripetal acceleration reaction is up in the up direction. We can find what that speed that it is for a necessary reasonable hill radius. And there again, the radius of the track I'll put at 1.25 meters. And we can tweak that later if we want to go a little higher or lower on the accelerations. We know the acceleration down is the gravity, 9.81 meters per second squared. Now the centripetal acceleration reaction, we know centripetal acceleration is v squared, velocity squared, divided by radius of the curve. We solve that. We've done this before. We times both sides of the equation by r. We get this, and then we take the square root. We're trying to solve for v, so we take the square root of both sides of the equation, and when you get velocity equals the square root of a times r. So plugging these numbers in for the radius, 1.25, we know acceleration is 9.81, and we get the square root of that, and we get 3.5 meters per second velocity over the top of that hill. So we want to be going 3.5 meters per second. If the mass is 10 kilograms, that would be 61 joules kinetic energy. Now the available at the top of the hill, the available potential energy was 184 joules, which is mgh, which is 10 times 9.81 times 1.875 height. That's 184 joules. The difference is 84 minus 61 is 123 joules, and that's what we've got left over, and we want to have that in potential energy at the top of the 0G hill. So we solve that. Potential energy equals mass times gravitational constant times the height. Height equals PE, potential energy, over 123 joules divided by 10 divided by 9.81. So the height is 1.254 meters right there at peak 1. If we make that 1.254 meters, we will see, and the radius is 1.25 meters, we will see gravity offset by the centripetal accelerations. And we'll feel a little weightless. Now we're going to change subject a little bit and talk about aerodynamic and mechanical drag. Whenever you put your hand out the window in a car, you feel this force on it, and as an object is translated through a fluid like air, you get a resistance, and it's dependent on what the shape looks like and the frontal area of the shape, and it dissipates as wind and eventually as heat. Mechanical drag is energy due to the moving parts, like the neoprene wheel squishing itself around your roller coaster rail or track. That kind of comes out as mechanical friction and heat. And even the bearings, though they have very little friction, they have a little bit of friction. And if you really run your wheels hard for a long time, you'll actually, roller coaster wheels heat up due to this friction between the wheels and the track. Now we have what's called a closed system, and we can define that. If the closed system was just the cart and the track, then we would be losing energy to where we didn't know. But we enclose the whole track, the cart, and the air around it in a system, and potential and kinetic energy is conserved within a closed system. Some energies turn to heat through aerodynamic drag and mechanical friction. So as it goes down the track, energy is traded. We talked about that last time. Some of the energy is changed into heat. Energy transfer is a function of speed. The faster you go, because the aerodynamic drag is actually a function of the speed. So when the speed gets pretty high, the aerodynamic drag goes up much faster in a nonlinear fashion. We can simplify things now and just say, look, this is a pretty slow system, relatively speaking, as far as aerodynamics goes, no more than 20 miles an hour. And for now, we're just going to average all the mechanical drag over the whole length of the track, just to make things simple. And I've verified that with the actual tracks I've made and come out with a number that represents how much energy is going to be given away and turned into friction and aerodynamic drag. So here's our track. We want to be able to calculate all of the things we've done in the past few pages, and maybe change the drag coefficient a little bit and see how our performance goes. Possibly we want to say, well, okay, we want to get over this hill, we want to go up here, and then we want to make it back over that hill once, back up to here, and then we want to go over the middle hill a second time, and then into over here, and rocking back and forth until we stop. Maybe that's a good goal, because that's a real long ride for a short track. Now, to perform all of these equations over the last 4 or 5 pages would take quite a bit of work to keep doing it and iterating on it. So we're going to employ a spreadsheet. And this is a spreadsheet for my first, which is very much similar to what we're doing here. My first roller coaster was a 2-dimensional out and back ride with a hump in the middle, just like this. And what I did was I made a spreadsheet. And so up here, I found out by testing that 4% is about the right amount of drag coefficient for these backyard roller coasters with a PVC track and polyurethane wheels. For example, what that means is if you had a track with a slope of 4% or 5%, I said here. In other words, for 100 meters, it drops 5 meters. That way the coaster would barely keep moving along that track. And so that's a 5% drop, 5% ratio, and that's just what that means. I have some constants up here, the gravitational constant and my mass I can put in. 20 kilograms is about 44 pounds. And then for each of these stations, the start, dip number 1, peak number 1, dip number 2, and then the run out, and then going backwards. So I have these different points. Starting at the peak, the height's 2.61 meters. That's the potential energy in joules. There's no kinetic energy because it's not moving yet. Down at dip 1, we see that we went down to 0.76 meters, and then that's the potential energy. The rest of it minus the drag must be kinetic energy, so now I can calculate the speed. So the velocity in meters per second is 5.7, about right at the bottom of that. And having a radius of 1.8 meters, the centripetal force is that, and you can see here I'm predicting in this track a little bit of negative G, so you're actually trying to come out of the cart for a little bit, and you'd want a seatbelt in there, which I did have. Dip number 2 is down here, and because we've dropped even further and the height is lower, we're actually having no potential energy because we're at the 0 point. And dip number 2, we have very little. We have a bunch of kinetic energy that translate to a pretty fast velocity there, 6.5 meters per second. And we get up to 2.63 centripetal acceleration plus or minus 1 g. We're over 3 g's, 3.7 g's down at the bottom here, which would be pretty exciting. We can make that higher by decreasing the radius here, or we can make it lower by increasing the radius. And that's that simple equation, the equation that we've talked about so many times. Velocity squared divided by r. A bigger radius makes a smaller force. A smaller radius makes a bigger force. More velocity, of course, makes a lot bigger force. Less velocity makes a smaller force. And the mass is the same. So this is a reversing. Over here, we don't really have anything going on other than it's at a certain height. And then it reverses and goes through dip 2 backwards, has some potential and kinetic energy, and it goes over peak number 1 backwards. That should say peak number 1. Peak number 1 backwards. And then it goes through dip number 1 backwards, and I didn't do any more calculating than that on here. But so a spreadsheet, basically, if you don't know what a spreadsheet is, you should find that out, because what it is it takes a bunch of numbers here and it multiplies them. So this is an equation. This is just a number, 2.61. This cell D6, has an equation in it, and this is the equation. It uses this number, and this number. And these dollar signs means relative or not relative position. If there's a dollar sign, it always uses that number. And this is useful when you're copying this equation somewhere else, which I did. I copied it down, and it kept moving down in some instances where there's no dollar signs. Well, you can find out about spreadsheets elsewhere. But this is a quick way of changing one parameter and then watching everything roll out. In other words, if I said I wanted to go 3 meters high instead of 2.61, all these numbers change all at once. I don't have to do all that calculating, and that's the power of a spreadsheet or a program. A code could do that. And you'll see that all of a sudden I'm going, oh, the velocity went up to 6.71. Well, actually 7 over 7, but I went above 4 G's in this second dip. But I'll switch it back to 2.61. So that is a spreadsheet that I use to make these recalculating go a lot quicker. So switching subjects here again. You want to find out what the radius is, and in other videos I show how to hot form the PVC 1.5 inch pipe with hot sand. You can also do it in sun if you're not trying to get too big of a radius, too small of a radius. And one method to do that is to just put a straight, like a 4-foot level across the curve, and by this equation you can find out what the radius is. So now we're ready to design and fabricate and operate our roller coaster. I'll start that in the next lesson.